simply 4.33 minus 4 divided by this, 7.3 minus 4. And we do the same for the lower end of the range. Get the difference and we get the probability. Okay, so I'm not going to go over this in too much detail because there's an example in the notes for the assignment. Okay, there's a worked example on how to calculate that. Okay, but again, just think big picture. Think big picture. Don't get lost in that right now. What we've got is you've got a recurrence relationship. We've divided, taking the maximum and the minimum values that we're interested on that current recurrence relationship. We've set up our bins that we're interested in to get our probability distribution. And then for each bin, we're going to calculate that probability, okay, from here, under this recurrence relationship. And then that probability is going to go here. Okay, and we'll end up with a distribution, okay? And obviously it's going to get smaller as the earthquake gets, as the event gets bigger, but that's what we expect. So we're going to end up with this. We do that for source zone 2 and 3 as well. Okay, so you're going to do the same thing, source zone 2 and 3. So this is kind of exactly what you need to do for your assignment, part 1. Except, again, I'll just reiterate that you're not given the equation. You're going to have to come up with you're going to have to come up with this equation first. I mean, that equation up there. You're going to come up with the source. You're going to have to come up with this equation. Okay. No, not that equation. Sorry. This equation, the recurrence. You're going to have to come up with the recurrence relationship. Okay, and you'll do that from you're going to do that from this. So this information, from this information there, for each of the sources, you're going to come up with one of these, the recurrence relationship. Okay, so that's the only difference. Now then once you've got your information, you've got your distributions, then it's just a matter of got all your distributions. Now this is using the equation. Okay, this is the PSHA equation we're going to use. So for source zone 1, okay, so remember for a hazard curve, okay, for a hazard curve, what have we got on a hazard curve? On the hazard curve, we've got, it's going to look like this, very simple. We've got an acceleration on the hazard curve, okay, and we've got an annual exceedance probability. How often is an acceleration going to be exceeded, okay, a year? Similar to this thing, we've got an annual exceedance probability, but it's in terms of magnitude. Now taking into account the 3 sources, we just want to be able to calculate what's the probability of a certain acceleration occurring, okay? It might look like something like this, okay? Now how do we plot that? We plot that by carrying out that calculation for PSHA on a number of target accelerations, okay? So these are what we call our target accelerations. Okay, so, sorry. These here are our target accelerations. Okay, these are our target accelerations. So basically, for each of these target accelerations, we have to calculate that equation. Okay, so when I say target acceleration, say for example in this case, source zone 1 with a target acceleration of equals 0.01 g. Okay, so what do we do to calculate for source zone 1? We need to calculate the peak ground acceleration for each combination of magnitude and distance. Okay, so we've got 10. So let's do it. Let's do it. I mean, illustratively, let's do it. So if we look here, source zone 1. For this distance, that distance, right, 27.04. Okay, source zone 1. Can I scrub this off now? Is that okay? Maybe I'll go over here. Okay. So for source zone 1,